Searching for a new home in space and leaving Earth is not only a long-cherished dream of humanity, but will eventually become a necessity for human survival. Mars is the planet that most captures our attention. Though it is small, its surface is filled with toxic gases, and it is an energy-poor planet. For a group of frustrated humans crammed into underground cities, this seems sufficient. But what if we dream bigger? What if we chose Venus, the most inhospitable and deadly place in our solar system, and turned it into our colony? Not to build floating cities, but to create a habitable second Earth. This might be simpler than you imagine. Venus currently holds the record for the hottest surface temperature in the solar system, reaching hot enough to melt lead. This intense heat stems from the solar system's most extreme greenhouse gas, carbon dioxide. CO excels at trapping heat. Even a slight increase in Earth's atmospheric CO concentration, from 510 to 510 makes us feel significantly warmer. CO makes up 590 of Venus's atmosphere. Furthermore, Venus's atmosphere is 10 times denser than Earth's. Standing on Venus's surface is like diving meters deep into the ocean. Under that pressure, you would be brutally killed instantly. It is truly a terrible place. So why go to all this trouble? First, and most importantly, Venus is nearly the same size as Earth and possesses 500 of Earth's surface gravity. Surface gravity is a critical factor in colonizing the solar system, as prolonged exposure to low gravity can be detrimental to health. Venus's size positions it as potentially the second and largest habitat in the solar system, a new home for billions of humans and trillions of animals. With oceans, lush forests, and beautiful skies, a well-transformed Venus could become the most beautiful place beyond Earth. Though we cannot truly terraform Venus, perhaps a slightly more ambitious future generation could undertake this project. Completing this monumental challenge would span generations, much like the pyramids built for our ancestors. This isn't the first time we've embarked on a project exceeding human scale. Alright, let's get started. First, we must cool Venus and remove its oppressively heavy atmosphere. As mentioned earlier, this gas mass is enormous, approximately 7 billion tons. How do we do it? We have several options. We could construct a massive solar collector to power a vast array of laser beams, heating the atmosphere until it explodes and disperses into space. However, this would require thousands of times humanity's total energy output and take millennia to clear the atmosphere. Another approach is to contain the atmosphere. By chemically transforming CO into different compounds, we could mine elements like calcium or magnesium from Mercury, then use a mass projector system. Electric orbits make rockets unnecessary on smaller planets. To blast them to Venus, the metals would bond with the CO, essentially permanently synthesizing various carbonates. But the sheer scale makes this impractical. Trillions of tons of material would be needed to sequester all the CO, which seems both wasteful and time-consuming. Another equally crazy idea is to literally shade Venus from the sun. Literally. We could use a giant mirror to block out the sun, thereby cooling the atmosphere. The mirror wouldn't need to be overly complex or heavy, just a very thin foil with some structural support. Constructing such a large, flat surface so close to the sun would effectively turn it into a solar sail, pushing it away from its position. So instead of one massive circular object, the mirror would consist of many distinct segments. Several angled ring mirrors could reflect sunlight from one to another. The mirrors would be tilted to reflect light until it is redirected back, balancing forces and keeping them all in place. After a few years of this infrastructure being in place, things would slowly begin, then intensify. In the first few decades, the atmosphere cooled slowly but remained dense and deadly. It wasn't until nearly 1,000 years later that temperatures reached the critical Shenshi. Suddenly, a great flood descended upon Venus. Under this pressure, carbon dioxide liquefied and began to rain. A global downpour of unimaginable scale persisted for century years, while atmospheric pressure and temperature began to plummet simultaneously. Nearly a century later, puddles had transformed into lakes and oceans. Surface temperatures had dropped to and atmospheric pressure was only 7 times that of Earth. Finally, at an extremely uncomfortable the CO oceans began to freeze, and rainfall turned to snowfall. What remained was a frozen Venus, covered in oceans as hard as rock and vast CO glaciers. At nearly 3 times Earth's atmospheric pressure, the atmosphere is now almost entirely nitrogen. If you don't mind freezing to death or suffocating, you could walk on Venus's surface today. But frozen CO still poses some problems at some point. We might want to warm the planet. But if we did, The frozen CO would melt and be released back into the atmosphere. So we need ways to prevent this. One is simply covering it all with cheap plastic insulation, and then covering that with ground-up Venusian rock or ocean. Though some planetary scientists would be very nervous about us building a new planet containing a potential time bomb, some unfortunate volcanic eruptions could instantly melt vast amounts of CO and ruin everything. Another obvious approach is to blast it all into space, then collect it on small satellites for future storage. We could use mass projectors more efficiently than rockets, but moving such massive quantities remains an intense challenge that will take time to solve. Regardless of how we solve the air issue, our next need is water, sourced from a frozen moon. Europa, Jupiter's moon, holds twice the water content of Earth's oceans. Capturing a moon and transporting it through the solar system is no simple feat. Instead, deploying a fleet of drones to carve ice blocks from Europa and using more mass projectors to fire them toward Venus might prove more feasible. Space tethers could save us considerable effort and energy. We made an entire video explaining how they work. In short, they are slings capable of carrying effective payloads at both ends. On Enceladus, they would handle most of the work to catapult ice toward Venus. The ice would hit Venus's tether and then gently fall like snow into its atmosphere. In exchange, Venus's tether could capture carbon dioxide ice erupting from below and accelerate it into orbit. We could use the same method to clear excess nitrogen, further reducing atmospheric pressure. Decades or centuries later, Venus would be covered by a beautiful shallow frozen ocean, hundreds of meters deep. It would look very different from today. Several continents and countless islands would have formed. It is starting to look a bit like our planet. Now begins the final and most ambitious stage of terraforming, making the air breathable and introducing life. First, we need light. We must reheat the planet. A Venusian day lasts down 10 hours, equivalent to Yayalu Earth days. So if we simply removed our giant mirrors, half the planet would be roasted. Even without thick air, temperatures would still climb to unbearable levels. The simplest way to create a day-night cycle and channel energy back in would be to use another set of mirrors to illuminate our continents and melt our oceans. This would give us complete control over the energy gained and where it goes. The atmosphere is now primarily nitrogen, with virtually no oxygen. The initial inhabitants could be trillions of cyanobacteria. They perform photosynthesis and release oxygen. We know this can rapidly transform our atmosphere because billions of years ago, they likely changed our young Earth's toxic atmosphere into an oxygen-rich one suitable for more complex animals. But that is not all. Cyanobacteria can perform nitrogen fixation, capturing nitrogen from the atmosphere and converting it into nutrients later used by life. In this way, they would essentially fertilize our dead seas and prepare the ground for more complex organisms. On land, our colonists would need to grind down some of the former Venusian surface to create soil for nitrogens and fixing plants to grow. Ultimately, billions of trees will spread, forming vast forests covering most of the continents. Venus will turn green, first the oceans, then the land. To accelerate this process, CO will be strategically released to feed the plants and cyanobacteria. Areas already covered in vegetation can receive extra light from our orbital mirrors, keeping plants active most of the day. Perhaps we won't need the same plants and animals we know today to accomplish this. As genetic engineering matures and our understanding of genetics and life mechanisms expands, we may design life only when needed. In any case, creating an atmosphere breathable for humans will take thousands of years. Meanwhile, you'll only need everyday clothing and an oxygen mask to stroll freely. Settlers will relish this vast new planet, abundant in resources and bathed in sunlight. They may devise novel ways to utilize the vast reserves of CO, ice, and nitrogen floating in orbit. Industrial processes, rocket fuel, and even facilitating terraforming of other planets like Mars. Venus has been fully terraformed. Animals roam across vast ecosystems. Cities are being built on a massive scale. Billions of settlers and their descendants call this world home. They see images of the past. How Venus was once the most inhospitable planet. How it took centuries to freeze this hellscape and sail across the oceans. And how it took millennia for people to breathe freely. They would find it utterly unbelievable. Okay, perhaps terraforming Venus isn't so straightforward, and many things must be done correctly in the future to make it a reality. But it is possible, and the technology is within reach for a slightly advanced humanity willing to venture into space. The only limit is our imagination.